In 1967, Andrew Viterbi invented what we know as the Viterbi algorithm, which is a programming algorithm that can estimate the likely sequence of events in a given situation. Originally, the focus was on digital cellular technology. However, the Viterbi algorithm is commonly used in everything from speech recognition to keyword spotting. Andrew is also a co-founder with Irwin Jacobs of Qualcomm, a leader of intelligent technology and innovation. In 2016, Andrew received the NAE Charles Stark Draper Prize for Engineering for development of the Viterbi algorithm, its transformational impact on digital wireless communications, and its significant applications in speech recognition and synthesis and bioinformatics. Joining me today is Andrew Viterbi, a pioneer innovator in the field of telecommunications. Andrew, thank you for joining me today.
All my pleasure and honor.
The Draper Prize is the highest honor awarded to an engineer in the United States. Please tell us something about your career path that led you to the accomplishments that ended up being cited in the Draper Prize.
Well, I went to school in Boston, all the way up through the public schools, and then on to MIT. And as soon as I had a reasonable start with a master's degree, I moved to California. And went to work fortuitously at JPL, the Caltech laboratory that at the time was a research center for the US Army Ballistic Missile Agency. But as soon as Sputnik was launched, which was 3 months after my arrival, everything opened up, and we were on the cover of Life magazine. That was quite an experience, and I learned a great deal about communications, and I also pursued a PhD at USC, which enabled me to enter academia, which had been my dream from the start.
What led you to move to California from the East Coast where you grew up and went to school?
Well, I would say, I should say, there was much more opportunity in new technology at the time in the aerospace industry. But the real driver was that I had aging parents. We were immigrants. I came when I was 4 years old, but my parents were approaching 60, and by the time I got a degree, they were approaching 75. And I decided that it would be a better climate, plus we had family in Los Angeles.
So your parents came with you.
Yes.
The Sputnik, I remember it as a junior high school student, and it really affected all of us, I think, in a way, and inspired a lot of us to go into science and engineering. I assume that's the same with you. I mean,
Yes, absolutely. It drove American R&D as a second phase from World War II. It was the government interest in science had diminished by 1957, and Sputnik rejuvenated it. And there's a great many people that entered science and technology because of that.
Now, you came over here, I think you said that at an age of 4 years old with your parents, and you came from Italy. You were born in Italy, okay? That must have been a challenging experience for a young boy.
For my parents, especially.
And your parents, too.
Yeah.
Did they speak English well?
Yes, eventually.
Eventually.
It didn't take me very long.
Do you still speak Italian?
I sure do. Yeah. I've even lectured in Italian universities.
Ah. I'm a chemical engineer, so I'm trying to get my arms around the Viterbi algorithm. I think I have some idea, but can you explain to everyone what it is and what it does?
Well, in simplest terms, it's a manner to protect digital transmission, that is, correct errors. It's one of a multitude of so-called error-correcting codes. And I took a path that was a little different than what was then popular, and it turned out that it was quite useful.
This was in, what, 1967? Is that right?
Starting probably in the mid-'60s.
Did you publish the?
I published it in April of '67.
So it was in the open literature, and then it's been used by many, many organizations and people since then.
It was the IEEE Transactions on Information Theory.
Now, you said you received your education in electrical engineering all the way
Yes.
through your doctorate. What led you to study engineering at the undergraduate level? What drove you into that?
Well, it was certainly the most popular major at MIT, and it still is. But I'd say that what attracted me was that it was more quantitative, more mathematical than most of the other fields at that time. And it was a lot of fun to proceed on that in that direction. My minor for the PhD was mathematics, and that helped me in the field of information theory and digital communication.
So mathematics was also of interest to you, and that led into an engineering interest as well.
And I was very much on the theoretical side to start out.
You know, of course, in high schools, you study science. You don't take anything in engineering, per se. So I think mathematics often leads some of us to study engineering when we go to college. But it's always a kind of a guess because you haven't had it before. Were you surprised when your freshman year, sophomore year?
Well, I was actually introduced by high school teachers who were very good. And I found in my freshman year what I was expecting and more, and gradually went into deeper, even abstract mathematics, which turned out to be very practical after all.
In 1985, you, along with Irwin Jacobs and some others, founded Qualcomm. You said that was your second company.
That was the second.
What was your first company?
Linkabit,
Linkabit.
which was acquired by a small conglomerate in Massachusetts called Maycom.
And then this was a second endeavor,
Yes.
which probably built on the first company in some sense. Right?
We had learned a lot, yes, in the first company.
And you and Irwin were both professors.
Yes.
And businesses are a little different than academia.
Yes, I would credit Irwin with better business preparation than I. He had started out at Cornell in hotel management and decided that was not challenging enough, and so he switched to engineering, I think, in his freshman year.
My first position was assistant professor at Cornell, and we used to eat in the Statler School of Hotel Management, where he studied probably. Qualcomm, how did the name come, Qualcomm? Where'd you get that name?
Quality Communications.
Quality Communications, yeah. And I think the big issue here was something called CDMA, and there was a rival protocol called TDMA. Can you talk a little bit about the difference, because CDMA eventually won out?
Well, the classical ways of separating different users is either in frequency, a different carrier frequency, or in time. That is, you give a slot to one user, which became popular as digital communications came in, and therefore you had to tie the ones and zeros, and as long as there wasn't too much of a gap, it could be blended into ordinary speech. But it was not as efficient as you would like for a number of reasons. The whole concept of cellular networks was great, but it caused interference among the cells. We were able to stuff a lot more users in a certain spectrum by using this concept of spread spectrum. That was really the technical term, but for public relations, they decided to call it Code Division Multiple Access, CDMA. And the concept, which goes way back to World War II, in fact, Hedy Lamarr had a patent in it, is to spread the bandwidth out much wider than the signal requires and make it look like background noise. And since our methods for recovering good data from noisy data, it was a natural phenomenon to take everybody's signal and make it look like noise. Now, that was great for getting, and therefore you were typically below the thermal noise background. Now the question is, how do you recover your own signal? Well, you use coding methods that will effectively spread the signal, a code that runs much faster than the data, and therefore it spreads the signal much more than the original data did. But to recover it, you then you use the same code for encoding as for decoding. And essentially it's a multiplication process. You multiply by this interferent looking signal, but if you know what the formula was, you have it and you can multiply it again and get back to the original.
The inverse problem, in a sense.
Yes. Yeah. And using CDMA, we were able to increase the number of users, or the number of users per cell, or the number of cells, by about a factor of magnitude, about 10 times. That was considered unbelievable. We had a lot of competition that said, you're violating the laws of physics. And but eventually it took us about better part of a decade to convince. We had a number of the major wireless carriers like Pacific Tel or New York, New Jersey Telephone, et cetera, that were on our side, and another equal number, I would say, that were unwilling to drop TDMA, plus the Europeans that have their own standard, and they had managed to get an agreement throughout the European Union, which was a first for them, and they were very proud of it. It was called GSM. And so that, I would say, the late 80s and all the 90s, we had that competition, and then by the turn of the century, CDMA was accepted by all. And there have been improvements on that, but it's always this spread spectrum concept.
So it's dominant now in the industry in telecommunications, CDMA.
What are they using in 5G? A variety, a variation on spread spectrum.
Now, I visited the museum you have at the Qualcomm headquarters, and Hedy Lamarr is featured in part of that museum. I think they used the term frequency hopping.
That's correct. That's another way of spreading the spectrum.
And she developed this. She was an engineer. For those younger folks out there, she was a very popular actress, a celebrity, and quite an engineer. And she donated her patent, I think, to the U.S. government.
Well, actually, yes. She was never trained as an engineer, but she had picked it up. She had an interesting history that people can see watching a documentary that was recently done. It was done very well. But she also had a partner in that patent and in the work, who was a musician and who had the idea of randomizing the signal by means of a player piano technology.
Yeah, the notes. Now, and her purpose in that patent was to foil espionage and
that's correct.
Stealing
and that, in
signals.
fact, was followed somewhat later. It was really after the war that the U.S. Army went into that technology very strongly. And in fact, our first company developed that kind of hardware for them.
A very interesting history there. And she's featured on our wall of outstanding female engineers and scientists at the NAS, National Academy of Sciences building in Washington, D.C.
Self-trained, self-educated. And presumably before she was an immigrant, she escaped from Austria, I believe, and her first husband was a munitions manufacturer. And she apparently got the, they say that she got the ideas from him.
Oh, interesting how ideas come. It also points out that engineering is about what you do, not about what you studied. You've transitioned from JPL to your position at UCLA as an academic professor, and then you've been in the business area, co-founding two businesses.
But I kept a foot in academia, an additional 20 years at UC San Diego.
UC San Diego.
On a part-time basis, of course.
But that's a very broad career there. You were just ready for opportunity, or did you plan this as your movements?
It was, one of our partners had a contact in the Naval Electronics laboratory, and I think they were our first founders, and we grew from there.
What advice do you have for a younger generation, people in college now, graduate school, in terms of following career opportunities and maybe innovation in general?
Well, I like to say to student audiences, find something that interests you and get deeply into it, and you'll find that you'll never working a day in your life. It'll be all fun.
Very good philosophy.
But it's tougher today. For one thing, education has become very expensive. And this is aside from all the other issues we have. It's a shame that students have to take loans or have to work very hard on a menial job in order to be able to pay for college. But the other thing is there are too many distractions. And you can be distracted if you're a humanities or liberal arts major. But in science and engineering, you better know what you studied in the last course, or you'll never pass the current one.
Mm-hmm. So the commitment to your education is a bit higher there in terms of formal education anyway.
And to have that commitment, it helps to find it interesting and
Yes.
and a pleasure to be in.
I like that characterization. If you find something, you're pursuing something that really interests you, you'll never work a day in your life. That's a very, very nice thought. And
I didn't make that up, but I thought it was a good.
Well, it doesn't
good piece
matter.
of
You
advice.
said it. we've got it recorded. So, do you have any advice in terms of what the National Academy of Engineering can do for the engineering profession, let's say, or?
Well, the National Academy is a very important institution in not only honoring, but in utilizing the talents and knowledge of the members for the benefit of the nation and of the world, particularly these days when we're trying to combat climate change and also some of our discoveries are evolutions like artificial intelligence, which has been around for a very long time, decades. I think from back in the days when I was a student, which is the previous century, the last half a quarter of the previous century, we had these periods where we were scared of what machines would do to us. Well, that was all nonsense until the memories became so large and the processing so fast that they can operate orders of magnitude faster than a human mind. But that doesn't mean they aren't still controlled by humans.
Yes, and the point you bring up too is sometimes we don't think hard enough about unintended consequences
Exactly.
of our advances. It doesn't mean you don't do it, but everything can be used for good or for bad.
And we have an example in wireless communication. Everybody now has a megaphone to the world.
Whether it's
And that
correct or
social
not.
media can be very dangerous and very damaging. And so we're already in it. What more can artificial intelligence do? Well, just pick up the papers and you read how it's corrupted.
Well, then maybe that pushes education at all levels to be a little more advanced in terms of getting people to think critically about what they hear and use some judgment in whether they accept everything.
And some legislation may be necessary
Yeah, some
on
legislation.
an international.
You talk about artificial
basis.
intelligence. I spent many years at Carnegie Mellon, and of course Herb Simon and Alan Newell and others there. I think there's something called the Dartmouth Conference that in the 50s where they were talking about AI. So you're right, it's really not new. It's just that with the
Becomes more and
electronic
more
advances,
feasible.
with the bandwidth, the electronic advances and scale, you're starting to be able to do things they could only dream about back then. But it's really a 70-year-old idea, maybe even older than that. Okay, well, Thank you very much for joining me. I appreciate it.
Pleasure.
And my pleasure too. Thank you.